Have you ever looked up at the night sky and wondered if we are truly alone in this vast universe? This question has captivated humanity for centuries, sparking our imagination and driving our curiosity to explore beyond the familiar boundaries of our own solar system. For generations, we could only speculate about what might exist among those distant points of light, wondering if other worlds like ours might be orbiting faraway stars. But what was once the realm of science fiction and philosophical pondering has now become one of the most exciting frontiers of scientific discovery: the search for habitable exoplanets. Just a few decades ago, we didn't have a single confirmed planet outside our solar system. Today, thanks to remarkable advancements in technology and astronomy, we've discovered thousands of these distant worlds, each with its own unique characteristics and mysteries. The hunt for exoplanets has transformed from a theoretical possibility into a vibrant field of exploration, where astronomers are not just finding planets but actively searching for those that might harbor the conditions necessary for life as we know it. These discoveries are reshaping our understanding of the cosmos and our place within it, offering glimpses into worlds that could potentially support environments similar to Earth. In this journey through the cosmos, we'll explore some of the most promising and fascinating exoplanets discovered so far, worlds that scientists believe could be habitable. From planets orbiting within the so-called Goldilocks Zone, where temperatures might allow for liquid water, to super-Earths with atmospheres that could potentially support life, we're about to venture into the extraordinary findings that have expanded our cosmic horizons. Each of these distant worlds tells a unique story and brings us one step closer to answering that profound question about whether we share this universe with other forms of life. So join me as we embark on this incredible exploration of the most habitable exoplanets found to date, and discover what makes each of them special in our ongoing quest to understand the possibilities that lie beyond our solar system. But what exactly are astronomers searching for when they label a distant world potentially habitable? It's far more than just finding a planet at the right distance from its star. The concept of habitability is built on a delicate and interconnected set of conditions, a checklist of sorts that we've derived from the only example of a living world we know, our own Earth. This framework helps us sift through the thousands of exoplanet discoveries to identify the most promising candidates for further study. The most famous of these criteria is the circumstellar habitable zone, often nicknamed the Goldilocks Zone. This is the orbital region around a star where temperatures are just right, not too hot and not too cold for liquid water to potentially exist on a planet's surface. This distance varies dramatically depending on the star itself. A fiery, massive blue giant star has a habitable zone much farther out than a cool, diminutive red dwarf. However, being in this zone is just the opening act. A planet's size and mass play a crucial role too. A planet too small, like Mars, struggles to hold onto a protective atmosphere, leaving its surface barren and exposed. A planet too large, often called a mini Neptune, might be shrouded in a crushing, gaseous hydrogen-helium envelope, making a rocky surface unlikely. The sweet spot seems to be Earth-sized or slightly larger, super-Earth planets, with enough gravity to maintain an atmosphere but not so much that they become gas giants. That atmosphere is itself a critical piece of the puzzle. Its composition acts as both a blanket and a shield. A robust atmosphere with the right mix of gases like nitrogen, carbon dioxide, and even traces of oxygen and methane can regulate temperature through a greenhouse effect and protect the surface from harmful stellar radiation. This leads us directly to the star a planet calls home. A star's stability is paramount. Many small red dwarf stars are prone to violent flares that could strip away a nearby planet's atmosphere and bathe its surface in lethal radiation, even if that planet orbits within the theoretical habitable zone. Finally, scientists consider geological activity. a molten core that drives plate tectonics and volcanic activity, is thought to be vital for recycling nutrients and regulating atmospheric gases over billion-year timescales. It's this entire symphony of factors: location, structure, air, and star working in concert that points us toward the worlds most worthy of being called Earth's cousins. So how do we actually find these incredibly distant and faint worlds, which are often billions of times dimmer than the stars they orbit? The methods astronomers have developed are nothing short of ingenious, turning seemingly impossible tasks into routine scientific procedure. One of the most productive techniques is known as the transit method. Imagine a tiny moth flying across a brilliant car headlight from miles away. Detecting the minuscule dimming of that light is the challenge astronomers face. When an exoplanet passes directly between its star and our telescopes, it causes a brief, minuscule dip in the star's brightness. By measuring these periodic dips, scientists can determine the planet's orbital period and even estimate its size. But the real magic happens when they analyze the starlight filtering through the planet's atmosphere during these transits. This allows them to detect the chemical fingerprints of gases like water vapor, methane, or carbon dioxide, providing crucial clues about the world's potential habitability. Another cornerstone of exoplanet hunting is the radial velocity method, which detects a planet's presence through its gravitational influence. A planet doesn't just orbit a star, the star also makes a much smaller orbit around the shared center of mass. This causes the star to wobble back and forth ever so slightly. As the star moves toward us, the light waves it emits are compressed, shifting slightly toward the blue end of the spectrum. As it moves away, the light stretches, shifting toward red. By meticulously measuring these subtle shifts in a star's light, astronomers can deduce the planet's mass and the shape of its orbit. While the transit method tells us a planet's size, radial velocity reveals its mass, and together, these two techniques paint a much fuller picture of what these distant worlds are like. For the most extreme cases, like very large, young planets orbiting far from their host stars, astronomers sometimes attempt the incredibly difficult feat of direct imaging. This involves using advanced instruments called coronagraphs to block the overwhelming glare of the star itself, allowing them to potentially photograph the faint dot of a planet. It's a bit like trying to see a firefly hovering right next to a massive searchlight from 1,000 miles away. An even more rare and opportunistic technique is gravitational microlensing. This occurs when the gravity of a star and its planet acts like a lens, bending and magnifying the light from a much more distant star behind it. This creates a temporary brightening that can be analyzed to reveal the presence of a planet. It's a method that doesn't require the planet to be close to us, allowing us to probe worlds across the entire galaxy. None of these discoveries would be possible without the incredible eyes in the sky we've launched. The Kepler Space Telescope was a true pioneer, staring relentlessly at a single patch of sky for years and using the transit method to find thousands of exoplanets, fundamentally reshaping our understanding of how common planets are in our galaxy. Its successor, the Transiting Exoplanet Survey Satellite, or TESS, is now conducting a vast all-sky survey, focusing on the brightest stars closest to us to find the best candidates for further study. And then there's the James Webb Space Telescope, a revolutionary observatory that is taking this research to an entirely new level. With its unparalleled infrared sensitivity, Webb can peer through the dusty clouds around stars and analyze the atmospheres of smaller, rocky planets in exceptional detail, searching for those biosignatures that might hint at the presence of life. These telescopes are the tools that have turned speculation into science and data into discovery. Now let's turn our attention to our very own cosmic backyard and meet Proxima Centauri b, the closest known exoplanet to Earth at just 4.2 light-years away. While that distance is still unimaginably vast in human terms, in the grand scale of our galaxy, it's practically right next door. This proximity makes it one of the most intensely studied and tantalizing worlds beyond our solar system. Discovered in 2016, Proxima b orbits Proxima Centauri, a small, cool red dwarf star that forms part of the triple-star Alpha Centauri system. What immediately captured the world's imagination is this planet's Earth-like mass. It's estimated to be about 1.3 times the mass of our own world, placing it firmly in the category of a rocky planet, a potential cousin to Earth. Its orbit is incredibly tight, completing a full journey around its star in just 11 Earth days. This is because Proxima Centauri is a faint red dwarf, and its habitable zone, the region where temperatures might allow for liquid water, lies very close in. So, despite its rapid orbit, Proxima b resides within this crucial zone, leading to hopeful speculation about the potential for liquid water on its surface. However, this intimate dance with its star comes with significant compromises that challenge the dream of a habitable world. The most profound issue is a phenomenon known as tidal locking. Just as our moon always shows the same face to Earth, it's highly likely that Proxima b is tidally locked to its star. This would mean one hemisphere is locked in perpetual, blazing daylight, while the other is frozen in an eternal, frigid night. The potential for life would then hinge on a thin, temperate twilight ring along the terminator line between these two extreme halves. An even greater threat to habitability comes from the star itself. Red dwarfs like Proxima Centauri are notoriously tempestuous, frequently erupting with powerful stellar flares and coronal mass ejections that unleash torrents of high-energy radiation and particles. A planet orbiting so closely would have its atmosphere and surface brutally bombarded by these events, potentially stripping away any protective atmospheric layer and sterilizing the ground. Any potential life would need to be extraordinarily resilient, perhaps existing deep underground or beneath protective layers of ice, to survive such a hostile stellar environment. Despite these daunting challenges, Proxima Centauri b remains a beacon of possibility, a symbol of our quest to find another Earth, and a prime target for future generations of telescopes that hope to one day peer directly at its enigmatic surface. While Proxima b offers a glimpse of a nearby world, the true crown jewel for exoplanet hunters lies a bit farther out, a system so packed with potential that it has fundamentally reshaped our ideas about where to look for life. 39 light-years from Earth, orbiting an incredibly faint and cool star, is the TRAPPIST-1 system, a family of not one or two, but 7 rocky planets, at least 3 of which are nestled perfectly within their star's habitable zone. This isn't just another planetary discovery, it's an entire solar system in miniature, offering an unparalleled natural laboratory for studying worlds beyond our own. The heart of this system is TRAPPIST-1 itself, an ultra-cool red dwarf star that is only about 9% the mass of our Sun and emits a mere fraction of its heat and light. If our Sun were a brilliant lighthouse beacon, TRAPPIST-1 would be the faint, glowing ember of a candle. This dim nature is precisely what makes its planetary system so extraordinary and so compact. All 7 known planets orbit their star at a distance closer than Mercury orbits our Sun. Their years are incredibly short, with the innermost world completing an orbit in just 1.5 Earth days, and the outermost taking about 20. If you lived on one of these worlds, you could celebrate your birthday every week. This proximity creates a celestial dynamic unlike anything in our solar system. From the surface of any one of these planets, the other 6 would appear in the sky not as distant points of light, but as clearly defined orbs, some even appearing larger than our moon does from Earth. You could potentially see the geological features and cloud patterns of your neighboring worlds with the naked eye, a constant, stunning reminder of your place within this tightly knit planetary family. The gravitational interactions between them are also significant, with each world gently tugging on the others, which helps scientists precisely calculate their masses and densities, confirming they are all rocky terrestrial planets like Earth, Mars, and Venus. The most thrilling aspect of the TRAPPIST-1 system is its potential for habitability. Because the star is so cool and dim, its habitable zone is shifted dramatically inward. Planets that would be scorched cinders if they orbited our Sun are, in this system, perfectly positioned for moderate temperatures. The planets designated TRAPPIST-1e, F, and G are considered the prime candidates. Based on density measurements and climate modeling, scientists believe these three worlds could have the right conditions for liquid water to exist on their surfaces. Some models even suggest that TRAPPIST-1e in particular might have a density and size most similar to Earth, making it a primary target in the search for a habitable environment. This system presents a breathtaking opportunity for a field of science known as comparative planetology. Instead of studying one isolated exoplanet at a time, astronomers can observe 7 worlds that formed from the same material around the same star at roughly the same time, yet have evolved down potentially very different paths. Why might one planet have held onto a thick atmosphere while another lost it? Could one be a barren rock while another is a vast water world? By comparing their atmospheres side by side, the James Webb Space Telescope and other future observatories can search for the chemical signatures of life across multiple planets simultaneously, giving us not just one chance to find a biosignature but several. The TRAPPIST-1 system is more than a collection of planets. It's a gift to science, offering a controlled experiment on a cosmic scale and bringing us closer than ever to answering whether we are alone. Of all the fascinating worlds in the TRAPPIST-1 system, one stands out as the most compelling candidate for a truly Earth-like environment, TRAPPIST-1e. This specific planet captivates astronomers because it strikes a remarkable balance of conditions that seem almost tailor-made for habitability, at least on paper. Its size and mass are nearly identical to our own world, making it one of the closest exoplanetary twins to Earth we have ever found. When scientists calculate its density from these measurements, everything points toward a rocky composition, a solid terrestrial world with a potential metallic core and a silicate mantle, not a gaseous mini-Neptune. This is the essential first ingredient, a solid surface upon which an ocean could rest and life could potentially take root. What truly sets TRAPPIST-1e apart, however, is its perfect positioning within the star's habitable zone. It receives an amount of stellar energy from its cool red dwarf sun that is strikingly similar to what Earth receives from our Sun. This optimal stellar irradiation is the magic number that could allow for liquid water to pool and flow on the surface, assuming the planet has developed a suitable atmosphere to regulate its temperature. It's a world that orbits in a thermal sweet spot, avoiding the scorching fate of its inner siblings and the deep freeze that likely grips its outer neighbors. This delicate balance makes it a primary target for scientists who model climates on distant worlds, and many of their simulations show that under a wide range of plausible atmospheric conditions, TRAPPIST-1e could maintain a temperate climate conducive to liquid water. This combination of Earth-like size, rocky makeup, and ideal energy intake elevates TRAPPIST-1e from being just another exoplanet to a world of profound significance. It represents our best opportunity within the system to search for the atmospheric signatures we associate with a living planet. The next generation of telescopes will be trained on this specific world, looking for the faint spectroscopic whispers of water vapor, carbon dioxide, methane, and perhaps even oxygen, a combination of gases that could hint at biological processes at work. While many challenges remain, from the potential impacts of stellar flares to the question of its actual atmospheric retention, TRAPPIST-1e embodies the thrilling possibility that a planet with Earth-like potential exists just a short cosmic journey away, offering a glimpse of a world that feels strangely familiar in a distant star system. While TRAPPIST-1e tantalizes us with its Earth-like potential, its neighbor, TRAPPIST-1f, invites us to consider an entirely different and perhaps even more fascinating possibility. A world not of familiar continents and oceans, but a vast global water world. This planet is notably larger and, crucially, less dense than its inner sibling, which points to a profoundly different composition. Scientists interpret this lower density as a strong indicator that a significant portion of the planet's mass isn't rock and metal but water and ice. We're likely looking at a world with a relatively small rocky core utterly engulfed by a monstrously deep global ocean, perhaps tens to hundreds of miles deep, making Earth's Mariana Trench seem like a shallow puddle by comparison. Its orbit places it a bit farther from the star than TRAPPIST-1e, in the cooler outer reaches of the habitable zone. This positioning suggests surface temperatures that are likely well below freezing. One compelling scenario is that TRAPPIST-1f is a snowball planet, its entire surface encased in a thick, global shell of ice. But beneath that frozen crust, the story could be dramatically different. The same gravitational tugging from its planetary siblings that helped us measure its mass could also provide a source of internal heat through tidal forces, flexing and warming the planet's interior. This heat, possibly combined with residual warmth from its formation, might be enough to maintain a vast, dark, liquid ocean beneath the icy surface, effectively creating a global-scale version of the subsurface oceans we believe exist on moons like Europa and Enceladus in our own solar system. This environment, while utterly alien to our surface-dwelling experience, opens up a thrilling avenue for potential life. A subsurface ocean protected from the stellar flares of its red dwarf sun by a kilometers-thick ceiling of ice could be a remarkably stable habitat. The water would be shielded from harmful radiation, and geothermal vents on the ocean floor could provide both the energy and the chemical nutrients necessary to fuel a biosphere entirely independent of sunlight. Life here wouldn't rely on photosynthesis but on chemosynthesis, much like the bizarre ecosystems found around hydrothermal vents deep in Earth's oceans. We could envision ecosystems of exotic organisms thriving in perpetual darkness under immense pressure, in waters that might have been liquid and stable for billions of years. The search for life on TRAPPIST-1f isn't about finding a second Earth. It's about discovering a second Genesis in an environment that challenges our very definition of a habitable world, proving that life, if it exists, can flourish in the most unexpected of places. Venturing much farther from our local stellar neighborhood, we travel 500 light-years into the constellation Cygnus to encounter a true pioneer in the search for other Earths, Kepler 186f. This world holds a special place in the history of exoplanet science because it wasn't just another discovery, it was a profound revelation. When it was confirmed in 2014, it earned the monumental distinction of being the very first planet of a size comparable to Earth ever found orbiting comfortably within the habitable zone of another star. This was the moment the search moved beyond theory and into tangible reality, proving that planets with the right size and the right location were not just possible, but actually existed out there in the great cosmic ocean. The planet itself is a fascinating subject. With a radius measured to be only about 10% larger than Earth's, it falls squarely into the category of a rocky terrestrial world, not a gaseous mini-Neptune. This Earth-like size strongly suggests a similar composition of rock and metal, a solid surface where landscapes could form and, crucially, where liquid water could potentially pool. Its orbit within the habitable zone of its star, Kepler 186, means it receives a level of stellar energy that could allow for temperatures suitable for liquid water to exist on its surface, assuming it has managed to develop and maintain a protective atmosphere. From a purely physical standpoint, Kepler 186f checks those two most critical boxes on the habitability checklist. It's the right size and it's in the right place. However, the star it calls home presents a very different picture of what life might be like there. Kepler 186 is an M-dwarf, a red dwarf star that is significantly cooler, smaller, and redder than our Sun. It's about half the mass and size of the Sun, and it emits a pale, ruddy glow. This means its habitable zone is located much, much closer in. While Earth enjoys a leisurely 365-day journey around our Sun, Kepler 186f completes its year in just 130 days, orbiting its star at a distance that would place it somewhere between Mercury and Venus in our own solar system. But because the star is so much cooler, this tight orbit is precisely what keeps the planet in that temperate, life-friendly region. A day on this world would be unlike any on Earth. The Sun in its sky would appear about a third larger than our Sun, but it would shine with only a fraction of the brilliance, casting a dim, orange-red light across the landscape. Some scientists have poetically suggested that the planet's noontime illumination might be similar to the level of brightness we experience on Earth just before sunset. This has led to widespread speculation that any photosynthesis-dependent plant life on the surface might evolve to harvest light from these different wavelengths, potentially coloring the entire landscape in deep shades of red and black instead of the familiar greens we know. Furthermore, the planet's orbital characteristics raise the possibility that, like many worlds around such stars, it could be tidally locked, with one side in constant daylight and the other in endless night. The most likely environment for habitability would then be in the eternal twilight of the Terminator line, the thin band that separates the two extreme hemispheres. The true legacy of Kepler 186f is not just about its individual characteristics, but about the door it kicked open for astronomy. Its discovery was a powerful proof of concept, demonstrating to the world that planets with Earth-like dimensions and orbital positions were not rare flukes but were waiting to be found. It validated the methods scientists were using and ignited a new wave of excitement and investment in the field, paving the way for the discoveries of thousands more exoplanets by the Kepler telescope and its successors. It taught us that habitable worlds can form around a wide variety of stars, not just Sun-like ones, vastly expanding the number of potential homes for life in our galaxy. While we may never know for certain what conditions are truly like on this distant pioneer, its existence alone is a beacon of possibility, a reminder that Earth-sized worlds in the Goldilocks Zone are out there waiting for us to find them. While Kepler 186f proved that Earth-sized worlds could exist in habitable zones, its discovery also hinted at a whole other class of promising planets, the so-called super-Earths. These are rocky worlds larger and more massive than our own, and they might just offer some unexpected advantages for life. A prime example of this fascinating category is Kepler 442b, a world located over 1,200 light-years away in the constellation Lyra. Discovered by the prolific Kepler Space Telescope, this planet immediately stood out from the crowd not just for being in the right place, but for how remarkably Earth-like its conditions appear to be on paper. Kepler 442b orbits a star that is noticeably different from our Sun. It's a K-type orange dwarf which is slightly cooler, smaller, and less luminous than our G-type Sun. While that might sound like a disadvantage, it actually comes with some significant benefits for potential habitability. Stars like this are known to be far more stable and longer-lived than the volatile red dwarfs we've discussed. They have much quieter personalities, with far fewer of the violent flares and radiation outbursts that could threaten a nearby planet's atmosphere. This inherent stellar tranquility gives any orbiting world a much better chance of holding onto its protective gaseous envelope and developing a stable climate over billions of years. The planet itself is classified as a super-Earth, with a mass estimated to be about twice that of our own world and a radius roughly one-third larger. This places it in an intriguing sweet spot. It's large enough to likely have active geological processes like plate tectonics, which are thought to be crucial for recycling atmospheric gases and regulating a planet's climate over long timescales. Its stronger gravity would also make it much more effective at retaining a substantial atmosphere, acting as a robust shield against stellar winds. At the same time, it's not so massive that it would inevitably become a gaseous mini-Neptune with a crushing, uninhabitable surface pressure. All evidence points toward Kepler 442b being a rocky world with a solid surface, a place where continents and oceans could theoretically exist. Its orbit is another point in its favor. It completes a journey around its star in 112 Earth days, placing it squarely within the star's calculated habitable zone. Most importantly, astronomers have calculated that it receives about 70% of the stellar energy that Earth gets from the Sun. This puts its energy budget remarkably close to our own, much closer than many other celebrated exoplanets. This level of irradiation is a powerful indicator that surface temperatures could be conducive to liquid water, especially if the planet has developed an atmosphere with a moderate greenhouse effect. It's not so little heat that the world would inevitably freeze over, and not so much that it would risk a runaway greenhouse effect like the one that scorched Venus. This combination of factors led scientists to assign Kepler 442b a very high Earth Similarity Index score, a metric designed to quantify how closely a planet's physical conditions match those of Earth. It ranks as one of the most Earth-like worlds we've discovered to date, even more so than some of the TRAPPIST-1 planets. The Kepler mission's role in finding this gem cannot be overstated. Its long, unwavering stare at a single patch of sky allowed it to detect the faint, periodic dimming caused by this distant world transiting its star, providing the data needed to unlock its secrets. While its great distance makes it a challenging target for follow-up atmospheric studies with current telescopes, Kepler 442b remains a benchmark discovery. It represents the tantalizing possibility that planets which are not quite Earth's twins, but perhaps its bigger, more robust cousins, could be common and even highly capable of hosting life as we know it. While Kepler 442b represents a super-Earth orbiting a stable star, another discovery showcases the incredible potential of a world that is almost a perfect Earth twin in size, orbiting a remarkably calm red dwarf. Just 100 light-years away in the southern constellation Dorado, we find the TOI 700 system and its outermost known planet, TOI 700d. Discovered by NASA, a transiting exoplanet survey satellite, or TESS, this world caused a wave of excitement because it was the first Earth-sized planet TESS found orbiting squarely within the habitable zone of its star. What makes this discovery so special isn't just its size or location, but the unique and promising nature of its parent star. TOI 700 is an M-dwarf red star, but it stands apart from the typically tempestuous reputation of its stellar class. It's exceptionally quiet and stable, showing no signs of the violent flaring activity that plagues stars like Proxima Centauri and threatens to strip away the atmospheres of their orbiting planets. This stellar calmness is a game-changer for TOI 700d's potential habitability. It means the planet has likely been spared the relentless bombardment of radiation that can erode atmospheres and sterilize surfaces, giving it a far better chance of holding onto the essential ingredients for a stable climate over billions of years. The planet itself is only about 20% larger than Earth, placing it firmly in the category of a rocky world with a solid surface. It completes an orbit every 37 Earth days, placing it in the optimistic region of its star's habitable zone where liquid water could exist. However, this close orbit almost certainly means the planet is tidally locked, with one hemisphere perpetually facing the star in endless daylight and the other turned away into eternal night. This presents a classic challenge for habitability, as one might imagine a scorching hot day side and a brutally cold night side, with only a thin sliver of twilight in between being potentially livable. But this is where the planet's potential atmosphere becomes the hero of the story. Scientists have used sophisticated climate models to simulate what conditions might be like on TOI 700d, and the results are profoundly encouraging. The models suggest that if the planet has a dense, Earth-like atmosphere, it could efficiently redistribute heat from the hot day side to the frigid night side through powerful global wind systems. This would prevent the extreme temperature contrasts that a simple tidally locked world would otherwise experience. Instead of a sharp divide, the entire planet could maintain a much more moderate and uniform global temperature. One particularly compelling simulation even suggested that under the right atmospheric conditions, extensive cloud cover could form consistently over the star-facing side. These clouds would reflect a significant amount of stellar energy back into space, effectively acting as a planetary sunshade to keep the day side from overheating, while simultaneously helping to trap and distribute warmth to the dark side. This could create a global environment where liquid water is not only possible but could be widespread across much of the planet's surface. The discovery of TESS 700d is a testament to the power of modern astronomy, combining the precise transit hunting capabilities of TESS with the predictive power of advanced climate modeling. It demonstrates that tidally locked planets are not automatically doomed to be barren wastelands. With the right star and a sufficiently robust atmosphere, they can be dynamic worlds with their own unique and stable climates. This expands our view of what a habitable world can look like and significantly increases the number of promising candidates in our galaxy, as quiet M-dwarf stars are the most common type of star by far. TESS 700d stands as a prime example of a nearby, Earth-sized world with all the right ingredients for potential habitability, making it one of the most important targets for future study with the James Webb Space Telescope, which will finally seek to determine if this promising world indeed possesses the atmosphere that models suggest could make it a true oasis. Now, let's journey to a world that challenges our very definition of a habitable planet, forcing us to reimagine the possibilities for life in forms we can scarcely conceive. 124 light-years away in the constellation Leo orbits K2-18b, a discovery that has sent ripples through the field of astrobiology, not for being another Earth twin, but for being something entirely and wonderfully different. This planet represents a whole new class of potentially habitable environments, a type of world we have dubbed Haitian planets, a portmanteau of hydrogen and ocean. The existence of K2-18b and the stunning data we've gathered from it suggests that the galaxy might be filled with habitable worlds that look nothing like our own, dramatically expanding the cosmic real estate where we might one day find signs of life. Unlike the rocky super-Earths and terrestrial planets we've discussed so far, K2-18b is technically classified as a mini-Neptune. It's significantly larger than Earth, with a radius about 2.5 times greater and a mass nearly 9 times more massive. This size and mass place it in a category that was once written off entirely in the search for life. Scientists had long assumed that a planet of this stature would be a gaseous world, lacking a solid surface and instead consisting of a thick, crushing atmosphere of hydrogen and helium over a potentially molten core, making it utterly inhospitable. But K2-18b has forced a complete re-evaluation of that assumption, proving that these larger worlds can possess their own unique and compelling brand of habitability. The true breakthrough came when astronomers turned the powerful instruments of the Hubble Space Telescope toward this distant world and made a historic detection. During transit observations, as starlight filtered through the planet's atmosphere, the spectroscopic data revealed the unambiguous fingerprint of water vapor. This was a monumental discovery, the first time atmospheric water vapor had been confirmed on a planet residing within the habitable zone of its star. It was a clear signal that this mini-Neptune was not the barren gas ball we might have expected, but a world rich with one of the essential ingredients for life as we know it. This is where the Haitian world concept truly comes to life. The model for K2-18b suggests a planet with a massive, hydrogen-rich atmosphere, far thicker than Earth's nitrogen-oxygen shield. Beneath this vast gaseous envelope, the pressure and temperature conditions could be just right to support a planet-wide ocean. Not a rocky seabed with scattered oceans like Earth, but a single, global, boiling hot water ocean, thousands of miles deep, enveloping the entire planet. The surface of this ocean wouldn't be a familiar boundary between liquid and air. It would be a gradual transition where the dense atmosphere slowly dissolves into the ocean beneath, with no sharp shoreline or solid ground in sight. The atmospheric water vapor detected by Hubble is likely the outermost layer of this immense aquatic realm, evaporating into the hydrogen-rich sky. This bizarre environment redefines the very meaning of surface. For any potential life, the habitat wouldn't be on the ground but suspended within this vast ocean or floating in its upper layers. Life could potentially exist in this liquid water realm, protected from the space above by the immense atmospheric blanket. While the surface temperature is estimated to be far hotter than Earth's oceans, it's a heat born of atmospheric pressure and internal energy rather than stellar irradiation. The concept of a habitable zone for a Haitian planet is also different. Because the thick atmosphere traps heat so effectively, a Haitian world could remain habitable much farther from its star than a rocky planet would, further increasing the number of possible candidate worlds. The implications of K2-18b are nothing short of revolutionary. It tells us that we cannot be myopic in our search for life, only looking for pale blue dots that mirror our own world. Entire categories of planets we previously dismissed could be teeming with exotic biospheres unlike anything on Earth. The upcoming observations with the James Webb Space Telescope are poised to study K2-18b in unprecedented detail, not just confirming the water vapor but searching for other key molecules like dimethyl sulfide, a gas on Earth that is only produced by marine life. Finding such a biosignature would be a strong, though not conclusive, hint that life has found a way even in this strange, dark, high-pressure ocean world. K2-18b is a powerful reminder that life is tenacious and that the universe, in its infinite creativity, may have devised forms of existence in environments we are only just beginning to understand. The groundbreaking observations of K2-18b didn't just stop at the initial detection of water vapor. They opened a window into the dynamic atmospheric processes of a world unlike any in our solar system. The Hubble Space Telescope's precise spectroscopic data revealed more than just a static presence of water. It provided clues to a potentially active hydrological cycle operating within this hydrogen-rich environment. Scientists analyzing the data suggest that this thick atmosphere could indeed host clouds, not of water droplets as we know them, but perhaps composed of water vapor or other condensable gases. In such a dense atmosphere, these clouds might even generate precipitation, though it would be a phenomenon far stranger than any rainfall on Earth. Instead of water falling to a solid surface, any condensed liquid would descend through the immense atmospheric layers until increasing heat and pressure cause it to vaporize again, creating a perpetual cycle of evaporation and condensation within the sky itself. This finding fundamentally shifts our perspective on where life could potentially arise. For decades, the gold standard in the search for habitable worlds was finding a rocky planet with a temperate climate and liquid water on its surface, an Earth analog. K2-18b shatters that paradigm. It demonstrates that a planet does not need a thin nitrogen-oxygen atmosphere or a rocky, continental surface to possess the key ingredients for life. A vast global ocean beneath a thick hydrogen-helium atmosphere presents an entirely new type of habitat, one that could be far more common in our galaxy than Earth-like worlds. This expands the habitable zone concept itself, because a thick hydrogen atmosphere is a superb insulator. A Haitian planet could maintain temperate conditions in its ocean layer even while orbiting much farther from its star than a rocky planet could, dramatically increasing the number of candidate stars we can consider. The most profound implication of these atmospheric findings is what they mean for biosignature detection. On a rocky exoplanet, scientists look for specific combinations of gases in a thin atmosphere that could be produced by life, such as oxygen and methane coexisting. But the environment of a Hycean world like K2-18b offers a different and potentially more robust set of targets. Its extensive, hydrogen-rich atmosphere is more transparent and easier to probe spectroscopically than the thin atmospheres of smaller rocky planets. More importantly, the model of a vast, uniform ocean could allow biological byproducts to build up to detectable levels more easily than on a world with diverse geology and weather patterns that might dilute them. Researchers are particularly interested in searching for methyl chloride and dimethyl sulfide gases that on Earth are produced primarily by phytoplankton and other marine life. Detecting such molecules in the atmosphere of K2-18b would be a powerful, though not definitive, indicator of biological activity happening deep within its dark global ocean. This world has effectively forced the astronomy community to broaden its search parameters and reconsider its definitions of habitability. It serves as a stunning reminder that life, if it exists out there, will have evolved to fit its environment, not ours. The conditions within that deep, pressurized ocean might be ideal for exotic biochemistry that we can scarcely imagine, potentially thriving around hydrothermal vents on the ocean floor, completely independent of sunlight. The upcoming observations with the James Webb Space Telescope are poised to take this investigation to the next level, conducting deeper spectroscopic studies to not only confirm the initial findings but to search for these more complex carbon-based molecules. K2-18b is no longer just an exoplanet. It has become a benchmark, a prototype for an entire class of habitable environments that we are only beginning to understand, proving that the recipe for life in the universe may be far more varied and inventive than we ever dreamed. Venturing into a truly exotic stellar neighborhood, we find Gliese 667cc, a super-Earth that offers a glimpse into the complex and dynamic environments that could exist in multi-star systems. Located a relatively close 22 light-years away in the constellation Scorpius, this planet doesn't just orbit a single star. It is part of a triple star system, a celestial dance that would create a sky unlike any other we've imagined. Its host, Gliese 667c, is a small, faint red dwarf around which the planet closely orbits, but the other two stars in the system, Gliese 667a and b, are a pair of orange dwarfs that orbit each other tightly while, as a pair, they circle widely around the red dwarf and its planet. From the surface of Gliese 667cc, the parent red dwarf would appear as a large, dull red orb in the sky. The two companion stars, however, would be visible as tremendously bright points of light, shining with the intensity of our full moon or even brighter, casting distinct shadows and contributing a significant amount of additional illumination to the landscape, even during the day. What makes this world so compelling is its firm placement within the habitable zone of its red dwarf sun. With a mass approximately 3.7 times that of Earth, it falls squarely into the super-Earth category, almost certainly boasting a rocky composition and a solid surface. Its orbit is very tight, completing a revolution in just 28 Earth days, but because its star is so cool and dim, this close distance is precisely what keeps it in that temperature region where liquid water could theoretically exist. This combination of Earth-like orbit and substantial mass makes it a prime candidate for holding onto a robust atmosphere, which would be essential for distributing heat and protecting any potential biosphere from stellar radiation. However, the climate on such a world would be incredibly complex. The additional light and heat from the two companion stars would add a fascinating and potentially destabilizing variable to the energy budget of the planet. There would be periods where the planet receives a relatively consistent level of energy from its primary star, punctuated by times when the brilliant companion stars are high in the sky, providing a significant boost of warmth. This could create seasonal effects that are not tied to the planet's own axial tilt, but to the orbital motions of the entire stellar trio. If the planet is tidally locked, a strong possibility given its close orbit, the extra heating from the companion stars could help moderate the extreme temperature differences between the permanent day and night sides, potentially warming the frozen darkness and making a larger portion of the world temperate. Conversely, if the atmospheric circulation is weak, these additional heat sources could create unpredictable and intense weather patterns. The potential for habitability on Gliese 667cc is a captivating puzzle. It demonstrates that life-friendly conditions might not be limited to simple, single-star systems. Instead, they could arise in more complex gravitational environments, adding another layer of diversity to the planets we consider worthy of search. While the constant gravitational pull from 3 stars could make the planet's orbit less stable over very long timescales, its discovery fundamentally expands our view of where we might one day find life, proving that even in a sky with multiple suns, the ingredients for a living world can still come together. And then there are the worlds that hover on the very edge of discovery, whose existence is debated within the scientific community, forcing us to confront the immense challenges of finding such tiny, distant objects. This brings us to the fascinating and controversial story of Gliese 581g, a planet whose very name evokes a sense of mystery and what could have been. Located just 20 light-years away in the constellation Libra, this potential world was announced with great excitement in 2010 by a team led by astronomer Stephen Vogt. They declared they had found the first exoplanet orbiting squarely within its star's habitable zone that was both rocky and had a mass very close to Earth. The team even gave it a poetic nickname, Zarmana's World. For a brief, thrilling moment, it seemed we had found our first true Earth analog, a neighboring world that could potentially host environments similar to our own. The discovery was based on over 11 years of painstaking radial velocity data collected from the Keck Observatory in Hawaii. This method detects the subtle wobble of a star caused by the gravitational tug of an orbiting planet. The data suggested the presence of multiple planets around the red dwarf star Gliese 581, and the signal for planet G indicated an orbit of 37 days right in the heart of the star's habitable zone. Its estimated mass was just 3 to 4 times that of Earth, strongly suggesting a rocky composition, and its calculated equilibrium temperature was tantalizingly similar to our own planet's. It appeared to be the holy grail of exoplanet hunting at the time, a world that was not just potentially habitable, but also Earth-like in its fundamental characteristics. However, this initial excitement was soon met with intense skepticism from other astronomers. A separate team, working with a different and extensive dataset from the HARP spectrograph in Chile, reanalyzed the same stellar system. They could not find a statistically significant signal for the proposed planet G within their data. The central issue at the heart of the debate is the nature of the star itself. Gliese 581 is a magnetically active red dwarf, and its surface is covered in starspots and roiled by activity. This stellar noise can create signals in the radial velocity data that mimic the gravitational pull of a planet. One team's groundbreaking discovery could very well be another team's misinterpretation of complex stellar activity. The scientific community remains divided. Some analyses continue to support the existence of Gliese 581g, while others dismiss it as a data artifact, a ghost in the machine born from the star's own temperamental nature. Yet, even if Gliese 581g were ultimately confirmed not to exist, its story is far from a failure. It serves as a profoundly important lesson in the rigorous and often painstaking process of science. The intense debate surrounding this world pushed the entire field to develop more sophisticated data analysis techniques to better distinguish between a true planetary signal and the natural variability of a star. It highlighted the critical need for multiple, independent observations and long-term datasets to confirm such delicate discoveries. This case study exemplifies how science self-corrects, how a bold claim is subjected to intense scrutiny by the broader community, and how this process, even when it leads to ambiguity, ultimately strengthens our methods and our understanding. The quest to find another Earth is a marathon, not a sprint, and each disputed detection like Zarmana's world sharpens our tools and refines our search, ensuring that when we do finally announce the first unequivocal Earth twin, we can do so with absolute confidence. Now, let's turn our attention to a world that has quietly become one of the most promising and intriguing targets in the entire hunt for habitable exoplanets. Just 49 light-years away in the constellation Cetus, orbiting a faint red dwarf star, lies LHS 1140b. This super-Earth doesn't always grab the headlines like the TRAPPIST-1 system or Proxima Centauri b, but among astronomers who specialize in this field, it is often spoken of with a particular sense of eager anticipation. Many consider it not just a candidate for habitability, but perhaps one of the very best we have yet found for answering the ultimate question. While other discoveries might be more Earth-sized or orbit brighter stars, LHS 1140b presents a nearly perfect combination of favorable conditions that make it a standout candidate for detailed study. The planet itself is a substantial world with a mass about 6 times that of Earth and a diameter roughly 1.7 times larger. This places it firmly in the super-Earth category. But unlike some larger planets that could be gaseous mini-Neptunes, extensive analysis of its density points conclusively toward a rocky, terrestrial composition. We are almost certainly looking at a world with a solid iron core, a rocky mantle, and a solid surface, a planet with real ground beneath its feet. Its orbit of 25 days places it securely within the habitable zone of its host star, receiving just enough stellar energy that surface temperatures could allow for liquid water, assuming it has an atmosphere capable of regulating heat. This combination of being a confirmed rocky world in the habitable zone is the foundational reason for the excitement surrounding it. However, what truly sets LHS 1140b apart from many other promising exoplanets is the unique nature of its parent star and the extraordinary opportunities this presents for observation. The star LHS 1140 is a red dwarf, but it belongs to a special subset known as an inactive M-dwarf. Unlike the flare-prone tantrums of stars like Proxima Centauri or TRAPPIST-1, this star is exceptionally quiet, stable, and well-behaved. It shows very little of the violent magnetic activity that causes catastrophic stellar flares. This stellar serenity is an absolute game-changer for the planet's potential to host life. A calm star means the planet's atmosphere has not been subjected to a relentless billion-year barrage of high-energy radiation and solar winds that could have eroded it away into space. This gives LHS 1140b a much higher probability of having held onto a thick, substantial atmosphere, a critical prerequisite for maintaining liquid water and a stable climate. This world offers a second crucial advantage for astronomers: its geometry. From our vantage point on Earth, the planet's orbit is aligned such that it transits directly across the face of its star. This transit is like a key unlocking a treasure trove of information. As the planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to our telescopes. By analyzing this filtered light with a technique called transmission spectroscopy, scientists can decipher the chemical fingerprints of the gases present in that atmosphere. They can search for the telltale signs of water vapor, carbon dioxide, methane, and even potential biosignatures like oxygen. This is where the star's inactivity becomes a double blessing. Not only did it likely preserve the atmosphere, but its calm nature also makes the spectroscopic signal incredibly clean and clear. A flaring star would create noisy, messy data that could obscure or mimic the delicate atmospheric signatures we're trying to detect. LHS 1140's stability means the signal from the planet's atmosphere stands out with remarkable clarity. Furthermore, because the star is relatively small and the planet is relatively large for its category, the transit event causes a more significant dip in starlight and allows more light to filter through the atmospheric rim. This creates a stronger, more easily measurable signal than we get from many other Earth-sized exoplanets around larger stars. For all these reasons, LHS 1140b has been earmarked as a top-tier, Priority 1 target for the James Webb Space Telescope. Webb's powerful infrared instruments are perfectly suited to probe the atmosphere of this world in exquisite detail. Its observations could potentially confirm the presence and composition of that all-important atmosphere, telling us if this planet is a barren rock, a shrouded Venus-like greenhouse, or a temperate world with conditions similar to early Earth. It represents a cleaner, clearer laboratory for atmospheric study than almost any other nearby rocky planet. While we dream of Earth twins, LHS 1140b offers something perhaps even more valuable in the short term, a golden opportunity. It is our best chance to answer the first, most fundamental question in the search for life beyond Earth. Does a rocky world in the habitable zone actually possess an atmosphere? The answer, soon to be delivered by Webb, will either be a monumental step forward or a sobering reminder of the challenges life faces in the cosmos. This quiet world holds secrets that could define the next decade of exoplanet science. Now, let's travel to a truly ancient stellar system and meet a pair of planets that offer a glimpse into a deep and potentially serene cosmic history. Just 12 light-years away in the constellation Aries, we find the Teegarden star system, home to two of the most Earth-mass exoplanets ever discovered. The star itself is a fascinating subject. It's a tiny, dim red dwarf, so faint that despite being one of our closest stellar neighbors, it wasn't even discovered until the year 2003. It's an incredibly old star, with estimates placing its age at around 8 billion years, which is nearly twice the age of our own Sun. This means its planets have existed in a stable environment for an almost unimaginable length of time, providing a timeline for life that is profoundly longer than the one we've had on Earth. Orbiting this ancient sun are two confirmed worlds, Teegarden star B and C. Both planets are truly remarkable because their masses are almost identical to that of Earth, making them some of the closest replicas of our own world in terms of sheer size and probable rocky composition that we have yet found. The inner planet, Teegarden B, completes an orbit in just 4.9 Earth days and is considered one of the most Earth-like exoplanets ever discovered based on its Earth Similarity Index score. It resides very comfortably within the star's optimistic habitable zone, receiving stellar energy levels that are strikingly similar to Earth's. Its sibling, Teegarden C, orbits a bit farther out every 11.4 days, placing it in the more conservative or extended region of the habitable zone, with an energy input closer to that of Mars. This positioning suggests a world that is likely much colder, but still holds potential for habitability under the right atmospheric conditions. A defining feature of this system is the gentle nature of its star. Unlike the violent, flare-prone red dwarfs we've encountered elsewhere, Teegarden's star is exceptionally quiet and stable, emitting minimal levels of harmful ultraviolet and X-ray radiation. For billions of years, these planets have likely been bathed in a calm, steady light, rather than being subjected to the atmospheric stripping tantrums of a more volatile star. This stellar tranquility is perhaps the single greatest advantage for the potential development and persistence of life on these worlds. It means any atmospheres they formed in their youth had a much stronger chance of surviving intact over these vast eons, providing a stable blanket to regulate climate and shield the surface. However, due to their extremely close orbits, both planets are almost certainly tidally locked, with one hemisphere perpetually facing the star and the other locked in eternal darkness. This presents the now familiar challenge of extreme temperature differences. But in this specific system, the potential solutions are incredibly compelling. The profound age of the system means there has been ample time for a thick, nurturing atmosphere to develop and for planetary processes to find an equilibrium. A dense atmosphere with efficient circulation could effectively distribute heat from the scorching day side to the frigid night side, potentially creating a wide temperate band in the twilight regions. Furthermore, the sheer length of time, 8 billion years, is a monumental factor. On Earth, life arose relatively quickly, but it took over 4 billion years for complex, multicellular organisms to evolve. The T-Godden star planets have had nearly twice that entire duration for chemistry to potentially transition into biology and for life to evolve into complex forms, all under the steady, constant glow of their placid sun. This combination of Earth-like mass, apparent orbital stability, a benign stellar environment, and an unimaginably long timeline makes the T-Godden star system one of the most captivating targets for the search for life. These aren't just planets that might be habitable today, they are worlds that have been potentially habitable for eras that dwarf the entire history of our solar system. They represent the possibility of life that is not just ancient but profoundly advanced, having evolved over time frames we can scarcely comprehend. As we turn our most powerful telescopes toward these ancient twins, we aren't just looking for signs of biology. We are peering into a deep, deep past, searching for answers in a system that has been patiently waiting long before our own sun even began to shine. While the T-Godden star planets offer the allure of immense age, another nearby world captures attention for its near-perfect Earth-like characteristics and serene stellar environment. Just 31 light-years from us in the constellation Cygnus orbits Wolf 1069b, a discovery that has quickly risen to the top of the list of the most promising habitable zone exoplanets. This world is a testament to the idea that sometimes the most compelling candidates aren't the ones with the most exotic stories, but those that present the cleanest, most straightforward set of conditions for potential life as we understand it. It represents a convergence of nearly ideal factors that make astronomers genuinely optimistic about its potential. What makes Wolf 1069b so special starts with its fundamental physical properties. Its mass is almost identical to that of Earth, clocking in at about 1.26 times our planet's mass. This is a crucial detail because it places the planet firmly in the category of a rocky world, almost certainly composed of silicate rock and metals with a solid surface. Unlike the larger super-Earths that might be mini-Neptunes or the intriguing but speculative Hycean worlds, everything we know about Wolf 1069b points to it being a terrestrial planet, a true cousin to Earth, Venus, and Mars in its basic structure. It completes an orbit around its host star in just 15.6 days, a year that flashes by in little over 2 weeks from our perspective. This incredibly short orbital period might initially suggest a scorching hot world, but the nature of its star completely changes that calculation. Wolf 1069 is a red dwarf, but it belongs to a specific and desirable category known as an inactive M-dwarf. This star is exceptionally quiet and stable, emitting very low levels of ultraviolet and X-ray radiation compared to its more volatile stellar siblings. Its habitable zone, the region where temperatures could allow for liquid water, is therefore located very close to the star. Wolf 1069b's tight orbit places it squarely in the middle of this life-friendly region, receiving about 65% of the stellar energy that Earth gets from the Sun. This level of irradiation is a powerful indicator that with a suitable atmosphere, this planet could maintain surface temperatures conducive to liquid water oceans, rather than being a frozen wasteland or a scorching desert. The calm nature of the host star cannot be overstated as a critical advantage for habitability. Many red dwarfs like Proxima Centauri or TRAPPIST-1 are prone to frequent and violent superflares, cataclysmic eruptions that blast out intense radiation and particles. These events can scour the surfaces of nearby planets, strip away their atmospheres over time, and make the development of life nearly impossible. Wolf 1069, by beautiful contrast, shows no evidence of such extreme activity. It's a gentle, older star that provides a steady and non-destructive flow of energy to its planet. This stellar tranquility means that if Wolf 1069b developed an atmosphere in its distant past, it has likely been able to hold onto it for billions of years, protected from the erosive power of a tempestuous sun. A stable atmosphere is the key to climate regulation, surface pressure, and protection from cosmic rays, making it the single most important factor for sustaining liquid water and potential biology. Due to its close orbit, the planet is almost certainly tidally locked, with one side permanently facing the star in endless day and the other in perpetual night. While this creates a challenge of extreme temperature contrasts, climate models suggest that a sufficiently dense atmosphere could work wonders. Robust atmospheric circulation would transport heat from the scorching day side to the frigid night side, potentially creating a wide band of temperate climate along the terminator region, the borderline between light and dark. In the most optimistic scenarios, this could allow for liquid water to exist across significant portions of the planet's surface, not just in a narrow sliver. All of these factors, its Earth-like mass and rocky composition, its prime position in the habitable zone, and the remarkable quiet of its host star, combine to make Wolf 1069b one of the most promising exoplanet targets identified to date. It doesn't have the complexity of a multi-star system or the exotic nature of a potential water world. Instead, it presents a clear, relatively simple, and highly encouraging set of conditions that closely mirror what we believe is necessary for a world to be livable. This is why it has become a priority target for the next generation of telescopes, most notably the James Webb Space Telescope. Webb's powerful instruments are ideally suited to attempt the delicate task of analyzing this planet's atmosphere during its transit across the face of its star. A successful detection could reveal the presence of water vapor, carbon dioxide, or even potential biosignatures, telling us for the first time whether a true Earth mass world in the habitable zone actually possesses the life-sustaining blanket of an atmosphere. Wolf 1069b stands as a beacon of possibility, a nearby world that offers perhaps our clearest and most direct window into understanding whether the ingredients for life are common around quiet red dwarfs, the most numerous stars in our galaxy. While we've explored planets around serene stars and in compact systems, some of the most compelling discoveries have been hiding in plain sight, waiting for a fresh pair of eyes to see them. This brings us to the remarkable story of Kepler 1649c, a world that serves as a powerful reminder of both human ingenuity and the tantalizing similarities some exoplanets share with our own home. Located 300 light-years away in the constellation Cygnus, this planet was not found through a new observation or a pioneering telescope, but by a team of volunteer citizen scientists painstakingly sifting through old data that automated algorithms had previously misclassified. Their discovery within the archived observations of the retired Kepler Space Telescope unearthed what many astronomers consider one of the most Earth-like exoplanets we have ever identified, a hidden gem lurking in the vast cosmic dataset. What makes Kepler 1649c so extraordinary is its striking combination of two key Earth-like qualities. First, its size is almost identical to our own planet, with a radius measured to be just 1.06 times that of Earth. This near-perfect match makes it overwhelmingly likely to be a rocky world with a solid surface, rather than a gaseous mini-Neptune. A world of this size could feature familiar landscapes of mountains, valleys, and most importantly, basins that could hold liquid water. Second, and perhaps even more crucially, its orbital position is impeccable. It orbits snugly within the habitable zone of its red dwarf star, receiving about 75% of the stellar energy that Earth gets from our Sun. This places its estimated equilibrium temperature in a range that could readily support liquid water on its surface, assuming it has developed an atmosphere with a composition similar to Earth. This combination of being both the right size and receiving the right amount of energy from its star makes it an incredibly compelling analog to our own world. The star it orbits, Kepler 1649, is a common red dwarf, which means the planet's year is incredibly short, completing an orbit in just 19.5 Earth days. This close proximity also means the planet is likely tidally locked, presenting the now familiar challenge of a permanent day side and a permanent night side. However, the amount of energy it receives is so comparable to Earth's that climate scientists are particularly optimistic about its potential. Models suggest that with a sufficiently dense atmosphere to distribute heat, large regions of Kepler 1649c could maintain temperate conditions, potentially allowing for liquid water to exist across a significant portion of its surface. Its location within the system adds another layer of intrigue. It shares its star with at least one other planet, a rocky inner world similar to Venus, making the Kepler 1649 system a miniature analog to our own inner solar system, with one planet that might be too hot and one that might be just right. The story of its discovery is a testament to the power of collective human effort. Sophisticated computer algorithms had initially scanned the Kepler data and flagged the signal from this planet, but mistakenly dismissed it as a false positive, a trick of the data. It was only when members of the Kepler False Positive Working Group, a project that enlists volunteers to visually inspect these algorithm-rejected signals, took a closer look that the truth was revealed. These citizen scientists, who may have been students, teachers, or amateur astronomy enthusiasts, noticed the subtle, repeating signature of a transit that the machine had missed. Their sharp eyes and dedicated work rescued this world from obscurity, proving that even in an age of advanced automation, human intuition and careful examination remain invaluable tools for scientific discovery. This world stands as a monument to curiosity, a hidden Earth-like planet found not by a massive new observatory, but by people who simply looked a little harder at what we already had. Moving beyond the compact orbits of planets around turbulent red dwarfs, we find a world that offers a dramatically different vision of a potentially habitable environment. 42 light-years away in the picturesque southern constellation Pictor orbits HD 40307G, a super-Earth that breaks the mold in several fascinating ways. While the majority of promising habitable zone planets we've discovered are found orbiting small, cool red dwarf stars, this planet circles a star that is noticeably more similar to our own Sun. This single characteristic alone sets the stage for a planetary environment that feels far more familiar and, in some key aspects, potentially more hospitable than the tidally locked worlds we've grown accustomed to discussing. The star HD 40307 is classified as a K-type orange dwarf. This places it in a stellar category that is often considered a Goldilocks star in its own right, not as small and faint as an M-dwarf red star, and not as large and short-lived as a massive blue star. It's slightly cooler, smaller, and less luminous than our Sun, but it shares a crucial trait: stability. Unlike the flare-prone red dwarfs that can unleash devastating bursts of radiation, this K-type star is far more sedate and gentle. It offers a steady, consistent flow of energy, providing a stable climate for any orbiting planets over billions of years. This calm stellar nature dramatically increases the chances that a planet could develop and maintain a life-sustaining atmosphere without having it relentlessly stripped away by stellar tantrums. This brings us to the planet itself, HD 40307G, a substantial world with a mass estimated to be around 7 times that of Earth. This firmly places it in the super-Earth category, but unlike some larger planets that might be gaseous, its density suggests a rocky, terrestrial composition with a solid surface. Its most striking feature, especially when compared to the planets we've just explored, is its orbital period. Instead of a frantic race around its star measured in mere Earth days, HD 40,307G completes a leisurely, more Sun-like orbit every 200 days. This longer year is a direct result of orbiting a larger, brighter star whose habitable zone is located much farther out. This greater distance from its host star is a significant advantage. It almost certainly means the planet is not tidally locked. It would experience a normal rotation, giving it a regular day-night cycle just like Earth. This rotation promotes stable and balanced weather patterns, preventing the extreme temperature contrasts that plague worlds with a permanent dayside and nightside. A planet of this size and mass brings its own set of intriguing possibilities. Its stronger gravity would make it exceptionally good at holding onto a thick, substantial atmosphere. This dense atmospheric blanket would be highly effective at distributing heat around the planet, smoothing out temperature variations and creating a more globally temperate climate. It could also provide a robust shield against cosmic radiation. Furthermore, the increased mass likely means a more active and longer-lasting geological cycle. A hotter interior could drive vigorous plate tectonics and volcanic activity, processes that are thought to be crucial for recycling minerals and gases between the planet's interior and its atmosphere, helping to regulate the climate over astronomical timescales. The potential environments on such a world are thrilling to consider. With a thick atmosphere, strong gravity, and a stable sun, HD 40,307G could be a planet of dramatic topography, towering mountain ranges and deep canyons shaped by the powerful gravitational forces. Its skies might be a dense, deep blue or perhaps even a different hue altogether, depending on the atmospheric composition. The surface could feature vast oceans, and the longer orbital period might even give rise to distinct seasonal variations. While it is undeniably a larger and more massive world than our own, it represents a compelling alternative model for habitability, one that operates on a grander scale but within a rhythmic, sun-like cycle that feels strangely familiar. It stands as a powerful reminder that Earth-like conditions aren't limited to Earth-sized planets orbiting red dwarfs, but can also emerge around stars that more closely resemble our own Sun, offering a broader and more diverse range of potential homes for life in our galaxy. Now, let's turn our attention to a world that may not always dominate the headlines, but has quietly established itself as one of our very best neighbors in the search for life. Just 11 light-years from Earth, in the constellation Virgo, orbits Ross 128b, a planet that embodies the idea that sometimes the most promising worlds are not the flashiest but the most stable. Discovered in 2017, this exoplanet immediately captured the attention of astronomers not for any single spectacular feature, but for its remarkably well-balanced combination of favorable conditions. It presents a compelling case for habitability built on a foundation of planetary moderation and stellar serenity, making it a top-tier candidate in the catalogue of nearby Earth-like worlds. What makes Ross 128b so intriguing begins with its physical characteristics. Its mass is calculated to be at least 1.35 times that of Earth, placing it firmly in the category of a rocky super-Earth. This is a crucial detail. It is almost certainly a terrestrial planet with a solid surface of rock and metal, not a gaseous mini-Neptune. A world of this size could feature familiar geological formations like mountains, valleys, and most importantly, basins where liquid water could potentially collect. Its orbit is remarkably compact, completing a full revolution around its star in just under 10 Earth days. But this rapid orbit is not a sign of a scorching world. Instead, it is the key to its potential temperate nature, all thanks to the unique star it calls home. That star, Ross 128, is a red dwarf, but it belongs to an exceptionally desirable class known as an inactive or quiescent M-dwarf. This stellar designation is the cornerstone of the entire system's potential. Unlike the violently flaring tantrums of stars like Proxima Centauri or TRAPPIST-1, this star is profoundly calm and stable. It exhibits minimal magnetic activity and has shown no evidence of the catastrophic superflares that can bathe nearby planets in sterilizing levels of X-ray and ultraviolet radiation. For billions of years, Ross 128 has likely provided a gentle, steady glow rather than a chaotic and destructive barrage. This stellar tranquility is perhaps the single greatest advantage for any potential life on its orbiting planet. It means that if Ross 128 be ever managed to form an atmosphere in its youth, it has had an excellent chance of holding onto that protective blanket over eons, shielding any potential oceans and regulating surface temperatures. Because the star is so cool and dim, its habitable zone is located very close in. The planet's tight 10-day orbit places it squarely within this region, receiving about 1.38 times the stellar energy that Earth gets from our Sun. While this is slightly more energy, climate models suggest that with an atmosphere possessing a reflective quality similar to Earth's featuring some cloud cover, the planet could easily maintain equilibrium temperatures that are perfectly suitable for liquid water. Its position is not at the extreme inner or outer edge of the zone, but comfortably within it, reducing the risk of tipping into a runaway greenhouse effect or a global deep freeze. The potential climate on this world is a fascinating subject for speculation. Given its close orbit, it is highly likely to be tidally locked, with one hemisphere forever facing the star in perpetual daylight and the other turned away into endless night. This would create a dramatic temperature contrast, but a sufficiently dense atmosphere could work to mitigate these extremes. Global wind patterns would act as a planetary heating system, transporting warmth from the scorching day side to the frigid night side. The most likely region for Earth-like temperatures would be in the twilight ring, the terminator line that separates day from night. Here, in an eternal sunrise or sunset, conditions could be mild enough for liquid water to persist on the surface. Some models even suggest that if the atmospheric pressure is high enough, liquid water could exist across a much wider portion of the planet, not limited to just the narrow twilight band. The significance of Ross 128b is magnified by its proximity and the calm nature of its star. At just 11 light-years away, it is one of our closest cosmic neighbors, making it a prime target for future study with next-generation telescopes. Its star's inactivity provides a clean, clear signal for astronomers attempting the delicate work of atmospheric spectroscopy. When the planet transits across the face of its star, the light filtering through its atmosphere will be relatively free of the noise caused by stellar flares, allowing for a much clearer reading of its chemical composition. The James Webb Space Telescope and future enormous ground-based telescopes like the Extremely Large Telescope will be trained on this world, searching for the telltale signs of water vapor, carbon dioxide, methane, and even oxygen. Ross 128b represents a different kind of hope in the exoplanet hunt. It may not be the most Earth-like in size or the most perfectly positioned in its habitable zone, but it offers a powerful combination of stability and opportunity. It is a world that has likely enjoyed billions of years of peaceful, uninterrupted evolution under a gentle sun. This longevity and calm give biology, if it ever began, an immense timeline to develop and thrive. It stands as a quiet, steady promise, a nearby world that embodies the idea that the most habitable environments may not be the most dramatic, but the most stable, offering an enduring sanctuary where the delicate chemistry of life could have taken root. This overwhelming prevalence of small, cool stars in our cosmic neighborhood is no mere coincidence. It reflects a fundamental truth about the composition of our galaxy. Red dwarf stars, also known as M-dwarfs, are the true rulers of the Milky Way. they are astonishingly numerous, making up an estimated 70 to 80% of all the stars in our galaxy. For every star like our Sun, there are at least 10 of these diminutive, ruddy suns. This sheer abundance alone makes them statistically the most likely place to find orbiting planets, simply because there are so many more of them to host worlds. When we peer into the night sky, most of the points of light we see are massive, brilliant giants, but the true, hidden majority of the galaxy's stellar population are these faint, small stars, too dim to be seen with the naked eye from Earth. This means our search for habitable planets is inherently biased toward these systems. We are looking for life where the real estate is most common, not necessarily where it is most ideally suited. Beyond their staggering numbers, these stars offer another colossal advantage for the potential development of life, time, an almost unimaginable amount of it. A star like our Sun has a total lifespan of roughly 10 billion years. It took life on Earth about 4 billion of those years to evolve from single-celled organisms to the complex biosphere we see today. Red dwarfs, in contrast, are the ultimate cosmic marathon runners. They burn their nuclear fuel at a much slower, more frugal rate due to their lower mass and gravity. As a result, their lifetimes are measured not in billions but in trillions of years. The universe itself is only 13.8 billion years old, meaning not a single red dwarf has yet come close to dying of old age. This offers any planets in their habitable zones a stability and a timeline for biological evolution that is simply incomprehensible. Life on such a world would have an almost limitless runway to arise, develop complexity, and adapt, free from the existential threat of its star ballooning into a red giant and vaporizing it. The star itself becomes a near-permanent fixture in the sky, a guarantee of energy for epochs that dwarf the entire current age of the cosmos. However, this promising picture comes with significant and daunting challenges. The very characteristic that gives red dwarfs their incredible longevity, their low mass and faintness, also dictates that their habitable zones are located extremely close to the star. A planet must huddle very near its sun to receive enough warmth for liquid water. This intimate proximity leads to a phenomenon known as tidal locking. Just as our moon always shows the same face to Earth, a planet orbiting this close to a red dwarf will almost certainly become tidally locked, with one hemisphere perpetually bathed in daylight and the other plunged into eternal, frigid night. This creates a dramatic and potentially hostile environment, with the day side relentlessly baked and the night side frozen solid. The only potentially temperate region would be a narrow twilight band, a ring of eternal sunrise or sunset circling the planet. For life to thrive, it would likely require a substantial atmosphere to efficiently distribute heat from the hot side to the cold side, preventing these extreme temperatures and creating a more globally moderate climate. An even greater threat comes from the youthful personality of many red dwarfs. Especially in the first few billion years of their lives, these stars are often prone to violent and frequent tantrums in the form of powerful stellar flares and coronal mass ejections. These eruptions unleash torrents of high-energy ultraviolet and X-ray radiation, capable of stripping away the atmosphere of a nearby planet and bombarding its surface with radiation levels that would be lethal to life as we know it. A planet like Proxima Centauri b is subjected to such events regularly, facing a stellar environment that would make the retention of a protective atmosphere and the survival of surface life incredibly difficult. This has forced scientists to refine their search, focusing not just on any red dwarf, but on older, more quiescent and inactive ones that have settled into a calmer, more stable phase of their immensely long lives, like Ross 128 or Teagardens star. Despite these formidable obstacles, the discovery of so many planets around red dwarfs has fundamentally revolutionized the field of astrobiology. It has dramatically expanded the number of potential homes for life in our galaxy, forcing us to broaden our definition of a habitable world. We can no longer only look for Earth twins orbiting Sun-like stars. We must now seriously consider the possibilities for life on tidally locked worlds, on planets with permanent day sides and night sides, and in systems where the sun in the sky is a deep red instead of a brilliant yellow. This shift in focus has spurred the development of sophisticated new climate models that explore how atmospheres might behave on such exotic worlds, how heat could be distributed, and where liquid water might persist. It has taught us that habitability is not a simple yes or no checkbox, but a spectrum of possibilities, a complex interplay between a planet, its atmosphere, and the star it calls home. The humble red dwarf, once overlooked in the search for other Earths, has become the central character in our story, proving that the most common places in the universe might also be the most likely to host the delicate chemistry of life. So how do we move from simply finding these distant worlds to determining if any of them are actually alive? This is where the search enters its most profound and challenging phase, shifting from astronomy to astrobiology. The answer lies not in capturing direct images of alien forests or cities, but in analyzing the very air these planets breathe. We search for atmospheric biosignatures, which are specific chemical fingerprints in an exoplanet's atmosphere that could be evidence of biological processes. It's a bit like a detective arriving at a house and instead of seeing anyone inside, noticing the telltale smell of freshly baked bread coming from the kitchen. It's a powerful, albeit indirect, clue that someone is home. The most sought-after biosignature is the combination of oxygen and methane. On Earth, these two gases are a powerful indicator of life because they rapidly destroy each other through chemical reactions in the atmosphere. Seeing them coexist in significant quantities means there must be a continuous, active source replenishing them. For oxygen, that source is overwhelmingly photosynthesis from plants, algae, and cyanobacteria. For methane, it's a variety of biological processes, including the activity of microbes in wetlands and the digestive systems of animals. Finding both together in an exoplanet's atmosphere would be an incredibly exciting, though not yet definitive, sign that something is actively producing them. Another key gas is nitrous oxide, which is produced almost exclusively by microbial processes in soil and water. While harder to detect, its presence would be another strong piece of circumstantial evidence for biology. But detecting these faint chemical whispers across light years of space requires a telescope of unprecedented power and precision. This is the primary mission of the James Webb Space Telescope. Webb doesn't take pretty pictures of these planets. Instead, it uses a technique called transmission spectroscopy. When a planet transits or passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us. Different gases in that atmosphere absorb specific wavelengths of this light. Webb's incredibly sensitive infrared instruments capture this dimmed starlight and spread it out into a spectrum, a barcode of light where each missing line corresponds to a specific molecule that absorbed it. By meticulously decoding this barcode, scientists can identify the unique fingerprints of water vapor, carbon dioxide, methane, and potentially oxygen. A positive detection of a potential biosignature would be a watershed moment for humanity, but scientists will be meticulously cautious before making any grand announcements. The first step would be to rule out all possible non-biological explanations or false positives. For example, oxygen can build up in a planet's atmosphere through the photochemical breakup of water vapor by starlight, a process called abiotic oxygen production. Similarly, methane can be released by volcanic activity. The true test will come from looking for context and complexity. A single gas like oxygen might be intriguing, but a suite of gases that are out of chemical equilibrium with each other, like oxygen, methane, and nitrous oxide all present simultaneously, would be far more convincing. Furthermore, detecting these gases on a rocky planet firmly within the habitable zone would make the biological explanation much more compelling than if they were found on a gas giant. Ultimately, the discovery of a convincing biosignature would not be the end of the search, but the glorious beginning of an entirely new era. It would tell us that the universe is likely teeming with life, fundamentally shifting our understanding of our place in the cosmos. It would immediately transform specific exoplanets, like those in the TRAPPIST-1 system or LHS 1140b, into the most important scientific targets in history, driving the development of even more powerful telescopes designed to study them in finer detail. We would finally have an answer to the ancient question of whether we are alone, and in doing so, we would embark on a new journey to understand what kind of life is out there and how it shapes the worlds it calls home. But the James Webb Space Telescope is only the beginning of this new era of exploration, the first powerful tool in a growing observatory network designed to probe these distant worlds. While Webb excels at analyzing the atmospheres of planets transiting in front of their stars, its capabilities are naturally limited to systems whose orbits are aligned edge-on from our perspective. To truly expand our search and see the full diversity of habitable worlds, we need telescopes capable of directly imaging planets, of pulling their faint light from the overwhelming glare of their parent stars. This is the monumental challenge that the next great observatory, the Nancy Grace Roman Space Telescope, is being designed to tackle. Scheduled for launch later this decade, the Roman Space Telescope will carry a revolutionary instrument called a coronagraph. This is a sophisticated system of masks, filters, and mirrors specifically engineered to block the blinding light of a star, allowing the much fainter light of any orbiting planets to become visible. It's akin to using your hand to block the glare of a street lamp to see a moth fluttering nearby. Roman's coronagraph is a technology demonstration, a critical first step toward directly imaging gas giant planets and potentially large Neptune-sized worlds. While imaging a true Earth twin might be beyond its immediate reach, the lessons learned from Roman's coronagraph will be absolutely invaluable. It will serve as a pathfinder, testing the advanced technologies and complex data processing techniques needed to one day snap that first portrait of a pale blue dot orbiting another star. The success of this instrument will directly pave the way for the even more ambitious missions waiting in the wings. Those future missions represent the true culmination of this decades-long quest. Concepts like the Habitable Exoplanet Observatory, or HAB-X, and the Large UV/Optical/IR Surveyor, known as LUVOIR, are now being meticulously studied by NASA and the global scientific community. These are not mere telescopes, they are envisioned as flagship observatories of a scale and power that will redefine our place in the universe. HAB-X is designed with a specific, profound goal: to directly image and characterize at least 25 potentially Earth-like worlds around Sun-like stars. Its design includes a massive external star shade, a separate, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of the telescope, perfectly positioned to block starlight and create a deep shadow of darkness, allowing the telescope to see the faint planets hidden within. LUVOIR is an even more ambitious concept, a behemoth with a primary mirror potentially 15 meters across, dwarfing the James Webb's 6.5-meter mirror. With such immense light-gathering power and resolution, LUVOIR wouldn't just detect exoplanets, it could begin to map them. We could move from detecting atmospheric gases to seeing surface features. It might be able to identify continents and oceans on another world, to detect the distinct spectral signature of chlorophyll or other surface vegetation, and to monitor seasonal changes in cloud cover and surface albedo. The data from these observatories would allow us to move beyond simply detecting biosignatures to understanding exoplanet environments holistically, studying their climates, weather patterns, and overall potential to support life over geological timescales. The journey from the first tentative detections of hot Jupiters to the potential for mapping the surface of an Earth analog within a few decades is a breathtaking testament to human curiosity and ingenuity. These future missions represent a coordinated, stepping stone approach to one of humanity's oldest questions. Each observatory builds upon the legacy of the last, with Kepler and TESS providing the target list, Webb conducting the first detailed atmospheric reconnaissance, Roman demonstrating the critical technology for direct imaging, and HAB-X or LUVOIR finally bringing these worlds into focus. Together, they form a grand strategy, a multi-generational effort to shift the search for life from the realm of philosophical speculation into a rigorous, data-driven field of science, bringing us closer than ever to knowing whether the light of life shines on any of the countless worlds strewn across the cosmic dark. The staggering discoveries we've made about these potentially habitable worlds inevitably lead to one of humanity's most ambitious and daunting questions: could we ever actually visit them? The heartbreaking reality is that these Earth-like oases, while feeling tantalizingly close on a cosmic map, are separated from us by a gulf of space so vast it defies human intuition. The very unit we use to measure these distances, the light year, tells the story. Each light year represents the distance a beam of light travels in one entire year, a staggering nearly 6 trillion miles. Proxima Centauri b, our closest known exoplanet, is 4.2 of these units away. That means even if we could build a spacecraft that traveled at the speed of light, the absolute universal speed limit according to the laws of physics, it would still take over 4 years to get there. And that's just to our next-door neighbor. Most of the promising candidates we've discussed, like TRAPPIST-1 or Kepler 1649c, are dozens or even hundreds of light-years away, placing them firmly out of reach for any kind of mission we can currently conceive. Our current propulsion technology only deepens the sobering reality of these distances. The fastest human-made object ever launched is the Parker Solar Probe, which uses the Sun's gravity as a slingshot to reach speeds over 400,000 miles per hour. That sounds incredibly fast, and it is within our solar system. But at that blistering pace, a journey to Proxima Centauri b would still take well over 6,000 years. Our chemical rockets, which have taken us to the Moon and propelled our rovers across the solar system, are simply inadequate for interstellar travel. They require enormous amounts of fuel to achieve relatively modest speeds, making them impractical for voyages spanning decades or millennia. This technological wall forces us to dream of entirely new forms of propulsion, concepts that currently exist only on drawing boards or in theoretical physics papers. Ideas like nuclear fusion rockets, which would use controlled atomic explosions for thrust, could potentially cut the travel time to a nearby star down to a century. Even more exotic are concepts like antimatter engines, where matter and antimatter annihilate each other to produce unimaginable energy efficiency. However, producing and containing significant quantities of antimatter remains a monumental scientific and engineering challenge, a hurdle we are nowhere near overcoming. Faced with these immense travel times, one theoretical solution is the generation ship. This would be a self-contained, world-like vessel capable of sustaining a human population for centuries or even millennia. The crew that departed Earth would not be the same crew that arrived. Multiple generations would be born, live their entire lives, and die during the voyage, all within the metal hull of the ship. This concept presents a web of profound ethical, biological, and social challenges. Could a closed ecosystem truly remain stable for 1,000 years, recycling all air, water, and nutrients without failure? What kind of society would evolve in such an isolated environment, completely cut off from the rest of humanity? The psychological impact on generations destined to live and die in the void between stars is almost impossible to predict. Furthermore, the ship would have to be incredibly robust, able to withstand micrometeoroid impacts, cosmic radiation, and the inevitable degradation of its systems over centuries without any possibility of outside help or resupply. It is a testament to human determination, but also a stark reminder of the sheer difficulty of the task. This has led scientists and science fiction writers alike to ponder shortcuts through the fabric of spacetime itself. The most famous of these is the wormhole, a hypothetical tunnel connecting two distant points in the universe. Popularized in movies and books, a stable, traversable wormhole could, in theory, allow a spacecraft to bypass the normal confines of space, effectively arriving at its destination almost instantly. The mathematics of Einstein's general theory of relativity does allow for such structures. However, the realities are far less comforting. Theoretical models suggest that keeping a wormhole stable and open would require the existence of a form of matter with negative energy density, something we have never observed and do not know how to create. Even if they do exist naturally, they would likely be incredibly unstable, collapsing the moment anything tried to pass through. While a fascinating area of theoretical physics, wormholes remain firmly in the realm of speculation, a potential key to the universe that we have not yet found and may never find. For now, and for the foreseeable future, these exoplanets remain treasures that we can observe and study from afar but cannot touch. They are cosmic jewels locked behind the unbreakable glass of interstellar distance. This reality, however, does not diminish their importance in the slightest. In fact, it reframes our mission. Our journey to these worlds will not be made by astronauts in spaceships, but by photons of light collected by the immense mirrors of telescopes like James Webb and its successors. We will explore them not with rovers, but with spectroscopy, unraveling the secrets of their atmospheres from hundreds of light years away. They are laboratories for understanding planetary formation, climate science, and the potential for life itself. Each new discovery pushes the boundaries of our knowledge and inspires new generations of scientists and engineers to tackle those seemingly impossible challenges of propulsion and physics. They are distant beacons reminding us that the universe is vast, filled with wonders, and that our curiosity to understand it is a journey that begins not with a launch but with a question. From the nearby promise of Proxima Centauri b to the deep oceans of K218b, each of these worlds has reshaped our very definition of a habitable environment. We began our search looking for a second Earth, a planet just like ours orbiting a star like our Sun. But the universe, in its boundless creativity, has shown us that life's potential is far more diverse and resilient than we ever imagined. We now know that habitable conditions might flourish on a tidally locked world bathed in eternal crimson light, within a global ocean buried beneath a thick hydrogen atmosphere, or on a super-Earth with gravity strong enough to hold onto a nurturing blanket of air for billions of years. Planets like TRAPPIST-1e and F taught us that entire families of temperate worlds can exist around a single, faint star, while the quiet stability of systems like LHS 1140 and Wolf 1069 revealed that serene stellar neighborhoods might offer the best chance for life to arise and persist. Each discovery has forced us to abandon our earthly prejudices and consider a broader, more wonderful spectrum of possibilities for what a living world can be. We are truly living in the golden age of exoplanet discovery. Just 3 decades ago, we didn't know if planets around other stars were common or rare. Today, we have confirmed thousands, with billions more estimated to fill our galaxy alone. This explosion of knowledge is a testament to human ingenuity, from the Kepler Space Telescope's relentless stare to the James Webb Space Telescope's revolutionary ability to sniff out the chemistry of alien atmospheres. We have moved from simply detecting these distant points of light to beginning to understand their weather, their composition, and their potential to host the chemistry of life. This isn't just a scientific revolution, it's a profound shift in our cosmic perspective. We now look up at the night sky with the certain knowledge that it is filled with worlds, each a unique experiment in planet formation, each with its own story to tell. The journey is far from over. In fact, it has just begun. The most thrilling chapters are yet to be written. The next generation of telescopes already on the drawing boards will push this frontier even further. They will move from detecting atmospheric gases to potentially identifying surface features, seasonal changes, and even stronger, more complex biosignatures. The question has decisively shifted from if there are other worlds like ours to what they are actually like. The great silence of the cosmos is being filled with data, with evidence, and with possibility. So stay curious, follow each new announcement, each new paper, each new image from the depths of space. We are all witnesses to one of the most profound quests in human history, the search for our place in the universe and for company in the cosmic dark. The answer to whether we are alone is out there, orbiting a distant star, waiting for the right moment and the right technology to reveal itself.